welcome back to my class in number theory. For today, we will show that any integer element of the set Z of integers is either an even number or an odd number. But before that, we define what is an even number and what is an odd number. We specify the conditions for an even number and an odd number to satisfy. We start with even number. We let n be any element of the set C. C is the set of integers. So n here is any integer. And we say that the integer n is even if n can be written as 2 multiplied by k for some k. That is, n is an even number, even integer, if n can be written as twice an integer k. K here is an integer. And also we say n from this equation is even if 2 is a factor of n, which is even. Or we say n is an even integer if n is a multiple of 2. Also, if we divide both sides of this equation by 2, we would get n divided by 2. So this means n equals 2k means that 2 divides n by definition of divisibility. By definition of divisibility, n equals 2 multiplied by k means that 2 divides n. And we write 2 divides n by definition of divisibility implies that n is equal to 2k for some k where k is an integer. We take an example. 24 is an even number because we can write 24 as the product of 2. 2 here is a constant, it's always 2. 2 times another integer. And in this example, the integer is 12. If you write 24 equals 2k, then divide both sides by 2, you will get k equals 12. Therefore, the integer 24 is an even number because it can be written as twice the product of 2 and k, where k is equal to 12. We now define add integer. We define add, let n be any element of the set of integers C. Therefore, n is any integer and n is an odd integer if n can be written as twice the product of twice of k, n can be written as the product of 2 and k plus 1, where 1 here is a constant and 2 here is a constant. And k can be any integer. Take an example. We show that 23 is an odd integer. If 23 is an odd integer, then it can be written as 2 times an integer k plus 1. In the definition of odd integer, we take n equals 23. By definition of odd integer, if 23 is odd, then it can be written as 2k plus 1. And from this equation, you can solve 4k. We transpose 1 to the left-hand side, we get 23 minus 1 equals 2k. Or 2k equals 23 minus 1, and 23 minus 1 is 22. And dividing both sides of this equation by 2, we get k equals 22 divided by 2, or 11. Thus, we have shown that 23 is an odd number because it can be written as 2 times k plus 1, where k is equal to 11. We have shown that there exists an integer k such that 23 is equal to 2k plus 1, and that particular value of k is 11. Show that any integer element of the set C of integers is either even or odd, but not both. An integer cannot be both even and odd at the same time. Prove that n element of C is the set of integers. Therefore, n here is any integer, can be negative integer, positive integer, or 0. And n is either even or odd. We let n be any integer element of the set C. Then by division algorithm, or the division algorithm theorem, when n is divided by 2, n can be written as 2 times q, where q is called the quotient, plus the remainder r, where the remainder r is greater than or equal to 0 but less than 2. In the original division algorithm, we say A is divided by B. When A is divided by B, then we can write A equals BQ plus R, where the remainder R is greater than equal to 0 but less than B. In this particular example, A is N and B is 2. So by division algorithm, when N is divided by 2, N can be written as 2 times the quotient plus the remainder R, where the remainder R is greater than equal to 0 but less than 2. And from this inequality, you can see that the possible values of R are either 0 or 1. 1 is less than 2 but greater than 0. And the other possible value of R is 0. 0 is less than 2 and 0 is equal to 0. There are two possible values of R as suggested by this inequality, which gives the restrictions for the values of R. And the possible values of R are 0 and 1. R can be either 0 or 1. If we take R equals 0, then this equation becomes N equals 2Q plus 0. And by property of the identity element for addition 0, any quantity added to 0 is the quantity. Hence, N equals 2Q. And this equation simplifies to N equals 2Q for some Q. And by division algorithm, there exists a Q, an integer Q. And we have shown that N is a product of 2 times that integer Q. Therefore, from this, we conclude that N is an even number if the remainder R is 0. Now we take the second possible value of R. R is 1. If the remainder R is 1, then the integer N is equal to 2Q plus 1. If R, the remainder R is 1, this becomes N equals 2Q plus 1 for some integer Q, and we are sure that Q exists because N is divisible by 2. By division algorithm, if N is divided by 2, there exists integers Q and R such that this equation is true and this inequality is true. And we have shown that if R is 1, N is equal to 2 times Q plus 1. And from this equation, we conclude that if the remainder R is 1, n is an odd number. By definition of odd number, or specifically by definition of odd integer. The same in the first part of the proof, if the remainder are equal 0, this becomes nq plus 0, and nq plus 0 is q, and we are sure q exists because n is divided by 2. There exists q and r such that this equation is true and this inequality is true. And by definition of even number, because n is equal to 2 times the integer q, we conclude that n is even if r is 0. And if r is 1, the integer n can be written as 2q plus 1. And from this equation, we conclude that n is odd number by definition of odd number. Now we combine the two results. If n is any integer, we conclude that n is an even number, and that happens when the remainder r is 0. Or n is an odd number, which happens when the remainder when r is 1, and the remainder r is 1 is obtained when n is divided by 2. And here the remainder r equals 0 is obtained when n is divided by 2. And n is even. When n is even, the remainder r is 0. And when n is odd, the remainder r is 1. And combining these two results, if n is any integer, then n is either even with remainder of 0 or odd with remainder of 1 when n is divided by 2. We conclude therefore that n integer n is either even or odd, but not both. An integer n cannot be both even and odd at the same time. It's either even or odd. And we put this shaded rectangle to indicate the end of proof. We take another example. Prove that n and n squared have the same parity. And here is any integer, element of the set z of integers. And we want to show that n and n squared have the same parity. And what is meant by parity? By parity, it means that if n is even number, even integer, then n squared is also an even integer. And if n is an odd integer, then n squared is also an odd integer. And that is what is meant by parity. Hence, the proof of this example will consist of two parts. In the first part, we show that n is even only if n squared is even. And the second part of the proof, we will show that if n is odd if and only if n squared is odd. These are the two parts of the problem that we have to show. We have to show that n is even if and only if n squared is even. And secondly, we have to show that n is odd if and only if n squared is odd. And I will show the proof for letter A, and for your exercise, please try to show letter B. You know, from your mathematical logic course, statement of this form is a biconditional statement. That means to show that n is even if and only if n squared is even, we have to show that if n is even, then n squared is even. And we also have to prove the converse of the first statement. If n squared is even, then n is even. And this is a a biconditional statement. Again, the proof of letter A. N is even if and only if n squared is even will consist of two parts. In the first part of the proof, we show that if n is even, then n squared is even. And the second part of the proof, if n squared is even, then n is even. This statement is the converse of the first statement. And this statement, the first statement, is the converse of the first statement. And if you combine these two statements, you get this biconditional statement. N is even if and only if n squared is even. We start with the first part, if n is even, because n is even by definition of even number, n can be written as 2 multiplied by k, where k is some integer. We are given that n is even, so we make use of this given. By definition of even number, n can be written as 2 multiplied by k, where k is some integer. N equals 2k for some k. And this is true by definition of even number because n is given as even number. And from this equation, we derive the value of n squared by taking the square of both sides. We start from the given n equals 2k, and we take the square of both sides. The square of n is n squared equals the square of 2k. Square of 2k by property of exponent. N squared equals the square of 2, 4, multiplied by the square of k, k squared. And 4 can be divided by 2. Hence, 4k squared can be written as 2 multiplied by 2k squared. Hence, from this equation, n squared is equal to 2 times 2k squared. And we let 2k squared be equal to h. Therefore, n squared is equal to 2h, 2 times h, where h is equal to 2k squared for some k. Because k here, we are sure that k exists, then h exists, and n squared is equal to 2 times h. And because n squared is equal to, is divisible by 2, is a multiple of 2, or n squared is equal to 2 times an integer h, then we conclude that n squared is also even number by definition of even number. We therefore conclude that n squared is even. That's by definition of even number, because we are able to write n squared as the product of 2 times h, where h is equal to 2k squared for some k. Now we will prove the converse of the first statement. We start now with n squared is even, and we show that n is even. Prove the converse of the first statement. In particular, we prove that if n squared is even, then n is even. And we make use of the given that n squared is even. By definition of even number, n squared can be written as the product of 2 and some integer, which we will denote by h. By definition of even number, we can write n squared equals 2 times some integer h. And this is true. This must be true because we are given that n squared is even number. In particular, I will take h as an integer equal to 2 times k squared. In particular, we take h equals 2 times k squared, and in this equation, we replace h with 2k squared. We have n squared is equal to 2 multiplied by h. H is 2k squared. This implies n squared is equal to 2 times 2 is 4 multiplied by k squared. And from this equation, we take the square root of both sides. The square root of s squared is equal to the square root of 4k squared. And the square root of n squared is equal to n. And the square root of 4 is 2 times the square root of k squared is k. So the square root of 4k squared is 2k. Therefore, from this equation, where n equals 2 times k, where k is some integer, we conclude that n is an even number by definition of even number. In the definition of even number, the integer n is even number if n can be written as 2 times some integer k. And we are able to write n as such as the product of 2 times k for some k. Therefore, in the second part of the proof, if n squared is even, we have shown that n is even. And this completes the first part of the proof, that n and n squared have the same parity, in particular if n is even, and then n squared is also even. Or using the biconditional statement, if n is even if and only if n squared is even. And for your exercise, please try to show that if n is odd, then n squared is even. If n is odd, then n squared is odd. Or in particular, using biconditional statement, you show that if n is odd if and only if n squared is odd. We now define addition modulo b. For b greater than 0, we define a modulo b equals r. This is read as a modulo b equals r. Also written as, using this symbol for addition modulo, a plus b addition modulo b equals r, where r is the remainder when a is divided by b. Hence, the value of a plus b addition modulo b, or a modulo b, is equal to r, where r is the remainder when a is divided by b. And by division algorithm, when a is divided by b, with remainder of r, a can be written as bq plus r, where the remainder r must be greater than equal to 0 but less than b. We take some examples. To find the value of the following, we start with number 1. Find the value of 15 modulo 4. In the definition, A is 15 and B is 4. And the value of 15 modulo 4 is the remainder when 15 is divided by 4. By division algorithm, when 15 is divided by 4, then we can write 15 as 4 multiplied by Q, the quotient, plus the remainder R. In the definition of division algorithm, A is 15, B is 4, and Q is the quotient, and R is the remainder. And we are interested in the value of the remainder when 15 is divided by 4. But by division algorithm, this equation must be satisfied as well as this inequality. And B here in our example is 4. So the remainder should be less than 4 but greater than equal to 0. And from this inequality, the possible values of the remainder are 3, 2, 1, and 0. And we use each of this value of R to find the value of Q, to find a possible value of Q. If R equals 3, then this equation becomes 15 equals 4Q plus 3. And solving for Q from this equation, we transpose positive 3 to the left-hand side. We get 15 minus 3 is 12 equals 4Q. And from this equation, we solve for Q by dividing both sides by 4. 4Q divided by 4 is Q. 12 divided by 4 is 3. Therefore, Q, the quotient Q is 3 when the remainder is 3. And that is one possible value of Q when the remainder is 3. Now we try to check if R is 2, if R is 1, if R is 0, if we will get another possible value for the quotient Q. If R is 2, this equation becomes 15 equals 4Q plus 2. And we transpose 2 to the left-hand side. At the right-hand side, we have 4Q. At the left-hand side, we have 15. Transpose 2 to the left-hand side, we take the opposite sign of 2, we get 15 minus 2 is 13. And from this equation, we solve for Q by dividing both sides by 4. Q is equal to 13 over 4. But in the definition of division algorithm, the quotient and the remainder are both integers. But 13 over 4 is not an integer, therefore we reject this value of Q. If R is equal to 1, This equation becomes 15 equals 4q plus 1. And we solve for q from this equation. We transpose positive 1 to the left hand side. At the right hand side, we get 4q equals 15 minus 1 is 14. And to solve for q from this equation, we divide both sides by 4. 4q divided by 4 is q equals 14 divided by 4. And 14 divided by 4 in lowest terms is 7 over 4. We divide 14 and 4 by 2, the greatest common factor of 14 and 4. But again, q must be an integer. Therefore, we reject this value of q, 7 over 2, because 7 over 2 is not an integer. Finally, we check r equals 0. If r equals 0, this equation becomes 15 equals 4q plus 0. And 4q plus 0 is 4q. So when r equals 0, this equation simplifies to 15 equals 4q, or 4q equals 15. And we divide both sides of this equation by 4. We get q equals 15 over 4. And again, we reject this value of q 15 over 4 because we require that q be an integer. Hence, there is only one possible quotient that is an integer, 3. And $15 now is equal to 4q plus r, where q is 3, and the remainder is 3. 15 equals 4 multiplied by 3 plus 3. By division algorithm, we are able to write 15 as 4 multiplied by 3, where 3 is q, the quotient, plus the remainder 3. R equals 3. Therefore, we conclude the value of 15 modulo 4 is equal to 3, where 3 is the remainder, when 15 is divided by 4 and 3 is the quotient. Note that you can also write 15 plus 4 is equal to 3. In regular addition, 15 plus 4 is 19. But here, 15 plus 4 is equal to 3 because we are using addition modulo 4. For our next example, we find the value of negative 7 modulo 3. In the definition of modulo, A now is negative 7 and B is 3. We want to find the remainder. The value of negative 7 modulo 3 is the remainder when negative 7 is divided by 3. By definition of division algorithm, when negative 7 is divided by 3, negative 7 can be written as negative 7 equals 3 multiplied by the quotient q plus the remainder r. Again, by division algorithm, when negative 7 is divided by 3, then we can write negative 7 as 3q plus r, where q is the quotient and r is the remainder, with the condition that the remainder r is greater than or equal to 0 but less than 3. And from this inequality, the remainder, the possible values for the remainder are 2, 1, and 0. And for each of this value of r, we find the value, the possible value of q. We start with r is 2. If r is 2, this equation becomes negative 7 equals 3q plus 2. And from this equation, we solve for the value of q. We transpose positive 2 to the left-hand side, we get minus 2. If r is 2, we get negative 7 equals 3q plus r is 2. And we solve for q from this equation, transpose positive 2 to the left-hand side, we have negative 7 minus 2 equals 3q. Or 3q equals negative 9. And dividing both sides of this equation by 3, we get 3q divided by 3 is q, and negative 9 divided by 3 is negative 3. And negative 3 is a negative integer, so this value of the quotient q is acceptable. We try r is 1. If r is 1, this equation becomes negative 7 equals 3q plus 1. And we transpose 1 to the left hand side. At the right hand side, we have 3q. 3q is equal to negative 7. Transpose 1 to the other side, we get minus 1 minus 7 minus 1 equals minus 8. And dividing both sides of this equation by 3, we get 3q divided by 3 is q. The right hand side, we have minus 8 divided by 3 is minus 8 over 3. And we reject this particular value of q because it is not an integer. Finally, when r is equal to 0, this equation becomes negative 7 equals 3q plus 0. And 3q plus 0 is 3q equals negative 7. From this equation, we solve for q by dividing both sides by 3. 3q divided by 3 is q equals negative 7 divided by 3, negative 7 over 3. And again, we recheck this value of q because q is not an integer. In the division algorithm, the quotient and the remainder are integers. And the remainder is required to be positive integer. So the only acceptable value of q is negative 3, and we now write negative 7 equals 3 multiplied by negative 3 plus r. Q equals negative 3 when r is equal to 2. Hence, when negative 7 is divided by 3, the quotient is negative 3 and the remainder is positive 2. And from this, we conclude that the value of negative 7 modulo 3, the remainder, when negative 7 is divided by 3, is 2. We therefore conclude that the value of negative 7 modulo 3 is 2. 2 is the remainder when negative 7 is divided by 3 and the quotient is negative 3. Or we write negative 7 plus 3 is 2 in regular addition. Negative 7 plus 3 should be negative 4. But in modular addition or addition modulo 3, negative 7 plus 3 equals 2 modulo 3. We take another example. We prove that B divides A if and only if A modulo B is equal to 0. 0 is the remainder when A is divided by B. And the proof of this will consist of two parts because the given statement is a biconditional statement. In the first part of the proof, we take B divides A, then we show that A modulo B is equal to 0. And the second part of the proof is the converse of the first part of the proof. In the second part of the proof, we take A modulo B equals 0, and we show that B divides A. And these are the two parts of the proof for our example. In the first part, we show that if B divides A, then A modulo B is equal to 0. And the second part of the proof is the converse of the first part of the proof. If A modulo B equals 0, then we show that B divides A. We start with the first part of the proof by definition of divisibility. If B divides A, then we can write A equals B multiplied by K for some integer K. We are given that B divides A, so we use the definition of divisibility. If B divides A, then A can be written as B times Q, where Q is some integer. And we have A equals BQ can be written as BQ plus 0. This is by property of the identity element for addition. You add any zero to a quantity is equal to the same quantity. Now, this is of the form A equals BQ plus R, where R now is the remainder. In the division algorithm, if A is divided by B, then A can be written as BQ plus R. But in this first part of the proof, R now is equal to 0, or the remainder R is equal to 0. And by definition of modulo, addition modulo, A modulo B is now equal to the remainder when A is divided by B, which is equal to 0. And this completes the first part of the proof. We have shown that if we are given that B divides A, we have shown that A modulo B is equal to 0. Now we show that the second part of the proof is also true. We show that if A modulo B equals 0, then B divides A. We use the definition of A modulo B. A modulo B we are given is equal to 0. This means that by definition of A modulo B equals 0 means that if A is divided by B, the remainder is equal to 0. And we denote the quotient when A is divided by B by Q. Again, by definition of A modulo B, if A modulo B is equal to 0, by division algorithm, if A is divided by B, the remainder is 0. And A can be written as B times the quotient plus the remainder 0. But BQ plus 0 simplifies to BQ. Again, by definition of A modulo B equals 0 means that the remainder is 0 and there exists some integer q such that we can write A equals BQ plus the remainder 0. And we are sure that there is some integer k such that this equation is true because this is true. This is true because we are given that A modulo B is equal to 0. And BQ plus 0 simplifies to BQ. And we are sure that there exists some integer q. Hence, by definition of divisibility, because A equals BQ, we say that B divides A. because there exists an integer q such that a is equal to bq. We conclude that b divides a. And we combine these two parts of the proof to conclude that b divides a if and only if a modulo b is equal to 0. Combining these two parts of the proof, we therefore conclude that b divides a if and only if a modulo b is equal to 0. And this completes the end of the proof for our last example. For your exercise, please try the following. Number 1, prove n is odd if and only if n squared is odd. The proof of this number 1 will consist of two parts because of this biconditional statement. In the first part of the proof, you show that if n is odd, then n squared is odd. In the second part of the proof, you take n squared is odd, then you show that n is odd. Number 2, calculate the following or find the values of each of the following. Letter A, 0 modulo 10. B, 10 modulo 123. C, 123 modulo 10. D, 457 modulo 33. E, negative 9 modulo 2. F, negative 3 modulo 7. And G, negative 5 modulo 5. In each of the following exercises for number 2, you do not have to try all the values of R. If you get, for a particular value of R, you get one possible value for Q, one acceptable, you get an acceptable value for Q, then you stop. Because for each of these numbers, there is only one remainder and one acceptable quotient value for Q. And that completes our lesson for today. If you have a question about the lesson today, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Calison, the channel of learning and leisure. And thank you for joining me in my class today in number theory.